Alright, we're going to be looking at one of the problems from the angular projectile motion assignment, and specifically this is the last problem on that assignment. I think it was problem number 4. I think it was the last one. I know it was the last one. I think it was problem number 4. Again, from the angular projectile motion assignment. And this is the one dealing with that child who's sliding down the slide with a water gun, and he's squirting the water gun as he's sliding down the slide, and they're giving you various pieces of information. So here's what's going on, okay? It says that he's sliding down a slide that has an incline of 45.0 degrees, okay? So that's our angle theta. And when he's firing this water gun, the water gun has an initial speed, because he's firing it horizontally, okay, has an initial speed of 11.1 meters per second, okay? It also turns out that this child is sliding down the slide at a speed, and we'll just call it our speed, I'll just write slide, speed of the slide, is equal to 11.1 meters per second, okay? They also give us some other information. They say that this child is, I guess we can just put it like this, the child is 1 meter, starts out at 1, and so that's our displacement in the x, starts out at 1, I think it was 0.00 meters from the ground, okay? And what they're wanting us to find here, oh yes, and they also gave us the time too. Oh, that's right. They gave us the time that it takes for, I think it was when he sprays the water gun, the time that it takes for the water to reach the ground, which is 0.329 seconds, all right? And what they're wanting us to find here in this problem is how far the water travels, okay? So they're wanting us to find our displacement in the x. That's what they're wanting us to look for here, okay? So let's take a look and try to decide first which equation is going to help us be successful here. Now, when you look through and choose from those 3 kinematics equations and then look at the x and y component that's going to be most useful, you'll find that this, well, let me back it up a little bit. Let me point at the hints first, all right, before we even talk about the equation. About the hints in this problem. The hints were saying that you need to find what the overall speed of the water gun is, right? What is the speed that the water is leaving? I mean, because they gave you the speed of the water gun, right, from which he's squirting. And they also went ahead and they gave you the speed that the child's sliding down at this 45-degree angle, all right? So, folks, since he's holding this horizontally, this is pretty much a horizontal projectile motion problem. I know this was underneath the angular projectile motion assignment, but this is a horizontal projectile motion problem, okay? And so that means that we need to figure out what our initial speed was and our x component, because the initial speed of the water gun, that 11.1, sprayed it, that's the water gun, the water leaving the gun. Now he's also sliding down the slide, and it's at an angle. He's not sliding, you know, straight horizontally, and he's not dropping straight down. He's sliding at an angle. So we need to figure out from this speed, we need to figure out what portion of this speed is of the x component, so that way we can add these together to get our total speed. So to actually solve for this guy, our delta x, we're also going to need our total speed. So let's look at an equation that can set us up for success here, all right? And so the equation that I think is going to help us do that is this guy right here, which is from our kinematics equation, our displacement in the x equals our initial speed multiplied by your change in time plus 1/2 acceleration times your delta t squared, all right? Now, if you went through all the equations like you should whenever you're doing any sort of projectile motion, the 3 kinematics equations breaking down the x and the y, you'd find that the one that we're interested here is the x component of this kinematics equation. So let me show you the x component of this, because this is horizontal projectile motion. Keep that in mind. So think about any object experiencing horizontal projectile motion, what some of the things are about initial speed and also acceleration, okay? So delta x is going to equal your initial speed in the x multiplied by your time plus 1/2 acceleration in the x multiplied by your time squared, okay? Now, check this out. Since this is horizontal projectile motion, yes, that's what we're trying to find, our displacement in the x. Yes, there will be, obviously there's going to be speed in the x component. And I know there's that part, but we also need to find what part of this speed is also in the x component, because you see how it's pointing an angle, partially in the y, partially in the x. So we need to find the x component of this. And we're going to ultimately figure that out too. Times our time, yeah, we have our time. Now, plus 1/2 multiplied by your acceleration in the x. Now, for horizontal projectile motion, well, actually even angular too, there is no acceleration in the x component. So this is 0. So 1/2 times your acceleration in the x times your time, it's all going to be 0 right here, okay? This is going to be gone. So when you rewrite the equation, it's delta x equals your initial speed in the x multiplied by your time, okay? So this is one of the equations here that's going to help us. Now, like I was saying, this speed in the x, we're going to need to figure this out, because specifically we're going to need the, I know it says initial speed, but the speed's going to remain constant throughout. Since this is horizontal projectile motion, the speed in the x is going to remain constant throughout this whole process, okay? So when we say speed here, we actually need our speed total, and that's going to be equal to the initial speed of the water gun, plus there's going to be some component from this speed of the slide. So we're going to need speed of the slide component, specifically in the x. So check out this speed over here, all right? Or check out this speed from when the kid's going down the slide. We can draw another diagram just looking specifically at that speed going down the slide. Now, check this. Do you see how it forms this angle of 45 degrees? If you're going to be saying, all right, I need to find my x component of the speed in the slide, speed in the slide in the x, and I also need to find my y component of the speed in the slide, y component, and then here of course is our speed from the slide itself. That's the resultant vector. This guy right here is the speed from the slide. You can say that since this is 45, it turns out that this angle right here is also equal to 45. So we know this side's known, and we want to find this side. So from this angle here, it's going to be opposite and hypotenuse. So when you look at SOHCAHTOA here, right, that SOHCAHTOA, the one that has hypotenuse and opposite in it is your, hypotenuse and adjacent. I'm sorry about that. Hypotenuse and adjacent. The one that has hypotenuse and adjacent in it is your cosine function, because cosine theta equals adjacent over hypotenuse, where specifically with our little diagram here that we're looking at, it's cosine theta equals our adjacent is the speed on the slide in the x divided by your just speed on the slide. That's the overall speed, the resultant or the net vector, okay? So what we're needing to solve for then is, because we just want this x side of it. Now remember, you can take this equation and plug in doing some algebraic manipulation. I'm going to go ahead and jump forward to doing algebraic manipulation, and then we're going to plug it in here too. So if you set this over 1, since they have an equal sign here, and cross multiply on both sides, you get your speed, and the kid's on the slide, and the x component is equal to your speed on the slide multiplied by cosine theta, okay? So this right here is what we're going to be plugging in for our speed in the slide. So check it out. You can rewrite this equation, because we need our initial speed right here. You can rewrite this equation by plugging all of this in for this part, this component. So let me rewrite it. When you combine all of those, here's what we get. Ultimate combination. We get our displacement in the x is going to be equal to your initial speed of the water leaving the water gun. Okay, I'll just put this in parentheses showing I'm substituting in. Plus, because this is being substituted in right here, and all this is being substituted right there, plus your speed on the slide, multiplied by cosine theta, and then see that's all been plugged in there, and we need multiplied by your change in time. So this, folks, is the ultimate equation that's going to lead you to success, all right? You don't need to do any further algebraic manipulation because we're trying to solve for our delta t. So this is the equation that's going to help you right here where we have that initial speed from the water gun they gave us. That was at 11.1 meters per second. Plus, because we needed the overall speed in the x component. So plus the speed going down the slide multiplied by cosine theta. Why does this work? Because we just wanted the x component of our child sliding down the slide because it gave that boost to the speed in the water gun. So we had to add all those together. And like we saw, because of using SOHCAHTOA, which is adjacent and hypotenused, we use the cosine function, all right? And so by plugging all of those in, this is the equation you want to use. So make sure you use the unit analysis properly, so that way you can make sure your units work out properly. Then you substitute and calculate, all right? Make sure you have the correct number of sig figs in your final answer. If you need more help, just come see me and we can talk about it one-on-one. Thank you.